Hi everyone. Earlier we have seen that if t is a self-adjoint operator and f is a continuous function defined on the spectrum of t, then we have shown that spectrum of f of t equal to f of spectrum of t. So that we call as a spectral mapping theorem for continuous functions. So let us recall. So if t is self-adjoint bounded operator and f is a continuous function defined on the spectrum of t, taking values in R, then we have shown that spectrum of f of t equal to f of spectrum of t. So this is nothing but a set of all f lambda, where lambda is coming from the spectrum of t. Now we want to ask the question, can we extend this result to normal operators? Can we extend the above result to normal operators? Okay. So the first step towards this is, if we take a polynomial in two variables, let us say p of z, z bar, can we say that spectrum of p of t, t star equal to p of spectrum of t? So we are going to prove that result in this lecture. Let t be a normal operator and p is a polynomial in z and z bar, then we can show that spectrum of p of t, t star is p of lambda, lambda bar, where lambda in the spectrum of t. Okay. To prove this result, we need one lemma. So let us look at that part. Okay. So let us take t to be a normal operator and 0 in the spectrum of t. Then we can say that then for any epsilon positive, there exists a closed subspace M having the property that if any operator commute with t star t, then M reduces that operator such that if B is commuting with t star t, then M reduces B and not only that, norm of t restricted to M is less than or equal to epsilon. Okay. So here there is nothing special about 0 in the, belongs to the spectrum of t. We can take any lambda in the spectrum of t, because lambda is spectrum of t is non-empty, so we can take a non-zero point also in the spectrum, and accordingly the proof will change. Okay. So let us write t star t as A. So as 0 is in the spectrum of t, now t is normal, so the spectrum equal to the approximate point spectrum. So we can get a sequence xj in the unit sphere of H such that txn converges to 0. So from this we can conclude that Axn also converges to 0. Hence Axn is nothing but t star txn is less than norm t star, that equal to norm t into norm txn goes to 0 as n tends to infinity. That means we can say that 0 is in the approximate point spectrum of A. But A is self adjoint, so that must be equal to spectrum of A. Okay, now let us look at a function which depends on the spectrum of T. Define f of t as 0 when mod t is bigger than or equal to epsilon, 2 into 1 minus mod t by epsilon when epsilon by 2 less than or equal to mod t less than epsilon, one when mod t is less than epsilon by 2. So we have a continuous function. We can draw the graph of this function. Okay. So let us look at, so this is minus epsilon by 2, epsilon by 2, epsilon, this is minus epsilon. Okay, after between minus epsilon by 2 and epsilon by 2, the function take value 1. In this interval, function takes value 1, and between epsilon by 2 and epsilon, the function takes value 2 into 1 minus mod t by epsilon. So this is a continuous function. So we can actually show that this is the graph. And after that, the function value is 0. Okay, so this is the graph of the function. So here the value is 1. So this graph is known as a truncated pyramid because it looks like truncation of a pyramid. Okay, now f is a real valued function which takes maximum value 1. Now let us define a subspace M. So define M as set of all x in H such that f of A x equal to x. Okay, so where f is given by this definition, and A is self adjoint, hence f of A we can use, using the functional calculus we can define f of A. Now the first claim we want to show is that M is non-zero. Okay. Now let us try to find the norm of the function. So consider norm of 1 minus f of A, identity minus f of A into f of 2a, since f is self adjoint, since a is self adjoint and f is real valued, f of a and f of 2a are self adjoint. So and they commute also, so we can show that, we can conclude that the operator in this norm is self adjoint. Hence, so the norm can be computed using the spectral radius supreme of 1 minus f of lambda into f of 2 lambda modulus, where lambda is coming from the spectrum of A. Okay. Now, if you look at the graph of the function, when the function when t is in the interval minus epsilon by 2, it takes value 1. So in that interval, this function 1 minus f lambda becomes 0. When t is in between epsilon by 2 and epsilon, then f of when lambda is bigger than epsilon by 2, 2 lambda becomes bigger than epsilon. So on one side it is bigger than 2 epsilon, on the other side it is smaller than minus 2 epsilon. Hence, the function value becomes 0 in both cases. So this value is 0, because when lambda is mod lambda bigger than epsilon by 2, then 2 lambda is bigger than epsilon. By looking at the definition, we can conclude that f of 2 lambda becomes 0. On the whole, this function value is 0. So this, from this we can say that the operator is 0. Hence, we can say that range of f of 2a is contained in null space of I minus f of a, but this is nothing but m. This is null space of I minus f of a. Now, since a is bounded operator, f of a is also bounded. So from this we can say that this is always closed. Okay. So m contains range of f of 2a, that is non-zero. Hence, we can conclude that M is a non-zero space. Okay. Next, we want to look at next claim 2 is that if B is an operator commuting with A, then M reduces B. If BA equal to AB, then M reduces B. So BA equal to AB, this implies that B into f of A is nothing but f of A into B. This comes from the functional calculus. Okay. So let us take x is in M. We want to show that Bx is also in M. Then x is in M means f of Ax equal to x. So we want to look at B of x. So B of x is nothing but B of x is nothing but f of Ax, because x is coming from M. Now this is nothing but f of A into B of x. So we have so therefore we can say that B of x is nothing, is null space of I minus f of A, and that is nothing but M. So this shows that M is invariant under B. B of M is contained in M. Now we want to show that M also is invariant under B star. So now BA equal to AB, this implies that B star A equal to AB star, because A is self adjoint. So this again, from this we can say that B star f of A equal to f of A into B star. Now apply the same procedure as earlier. So we can conclude that M is invariant under B star. Hence we can conclude that M reduces B. So, next claim is that we want to show that T restricted to M and norm of that is less than or equal to epsilon. So, claim 3. Norm of T less than or equal to epsilon or some term involving epsilon. So, here we show that it is epsilon by 2 square root of epsilon. So, let us take x coming from the unit sphere of M. Then we can show, then we have Ax. If you look at norm Ax is nothing but norm A f of Ax, because when x is coming from M, f of Ax equal to x. So, this is less than or equal to norm of A into f of A. We know that A into f of A is a self-adjoint operator. So, we can say that this is supreme of lambda f lambda, where lambda is coming from spectrum of A. In fact, A is a positive operator. Okay. Let us look at lambda into f lambda here. So, from that we can say that mod lambda into f lambda is less than or equal to epsilon. Okay. So, hence we can have norm T x square, because we want to look at T restricted to M, norm of that. This is nothing but inner product Tx with x, Tx. So, this is T star Tx inner product with x. This is Ax, and again this is less than or equal to norm A into norm x square. But we know that norm A less than or equal to epsilon. So, we can conclude that norm of T restricted to M is less than or equal to square root of epsilon. Okay. So, this completes the proof of this lemma. Now, using this lemma, we want to show that the spectral mapping theorem for polynomials. Okay. Now, let us look at the proof of the theorem. So, let us take lambda in the spectrum of T, and we know that this is exactly the approximate point spectrum of T. So, hence there exists a sequence xj in the unit sphere of H such that T minus lambda I acting on xj goes to 0 as j going to infinity. Now, since T is normal, we can say that T star minus lambda bar I acting on xj also goes to 0 as j going to infinity. That means, whenever lambda is in the approximate point spectrum of T, lambda bar is also in the approximate point spectrum of T with the same approximating sequence. Now, let us look at P of T star minus P of lambda bar I. We want to show that this is not invertible. So, this is nothing but summation mn equal to 0 to k. So, this polynomial we can write as a n m t power n t star power m minus lambda power n, lambda power m identity. So here P of z bar is nothing but summation mn equal to 0 to k a n m z power n z bar power m. So this is a polynomial in two variables. So in the corresponding operators will be written as above. Now we can write this as summation mn equal to 0 to k a n m t power n t star power m. We can add and subtract the term t power n lambda bar power m plus t power n lambda bar power m minus lambda power n lambda bar power m identity. So this can be written as summation mn equal to 0 to k a n m. We can take t power n out. So this is t star power m minus lambda bar power m identity plus, if we take lambda bar power m out, you will get t power n minus lambda power n identity. So we will get a n common for all these things. Okay. Now let us look at the earlier sequence xj and evaluate this operator at that point, that sequence xj. So next consider. So we can say that p of t star minus p of lambda bar identity and acting on xj is nothing but, so here the same thing we can write down summation mn equal to 0 to k a n m t power n into, so we can using the binomial theorem we can actually write down t star power m minus lambda bar power m. So this t power n into t star minus lambda bar I into t star power m minus 1 so on plus lambda bar power m minus 1 identity plus summation mn equal to 0 to k a n m. So we can take lambda bar power m. Here we can take t minus lambda I into t power n minus 1 plus so on lambda power n minus 1 identity. Okay. Everything acts on xj. This acts on. Now if you look at norm of this whole thing we can write down, and we know that these operators commute. This operator commute, and this commute. So we can say that, so therefore norm of p of t star minus p of lambda bar identity acting on xj is less than or equal to, so less than or equal to, so we can write some k1 into norm of t star minus lambda bar I acting on xj plus k2 into norm of t minus lambda I acting on xj. So we can actually say in the first term we can take t star minus lambda bar I to the right side, and that will act on xj, and remaining are bounded operators, they are less than or equal to k1, and none of those operators are less than k1. Similarly for the second one. So where k1, k2 are finite quantities, but we know that this goes to 0 as j going to infinity, because t star minus lambda bar I acting on xj goes to 0 and t minus lambda I acting on xj goes to 0. So this implies that p of lambda bar is in the approximate point spectrum of p of t star, but p of t star is normal. So this is exactly the spectrum of p of t star. So we have shown that whenever lambda is in the spectrum of t, p of lambda bar is in the spectrum of p of t star. Now we want to show the other way. Let us take mu from spectrum of p of t star. So then we can say that if you define operator b like this, p of t star minus mu times identity, this is not invertible. Hence we can say that 0 is in the spectrum of b. Also b is normal. Now we can apply the earlier lemma. So by the earlier lemma, so there exists for each n in n, there exists a reducing subspace Mn for each operator S commuting with b star b, and norm of b restricted to Mn is less than or equal to 1 by n. This is by the earlier lemma. Now in particular, so note that t commutes with b star b. Because t is normal, from that we can say that t commutes with b star b. Now let us write down Tn, t restricted to Mn, because it's a reducing subspace. Now this map is from Mn to Mn only, and this is also normal because each Mn is reducing. So here use the following result. If A is normal and M reduces A, then we can say that A restricted to M, which is a map from M to M, is also normal. Okay. Now let us take lambda n from the spectrum of Tn. Then we can find there exists some yn in the unit sphere of Mn such that Tn minus lambda n identity acting on yn. So this is nothing but t minus lambda n acting on yn, because Tn is nothing but t restricted to Mn. Whenever yn is coming from Mn, Tn yn equal to Tyn. So we can make this less than 1 by n for every n in n. So because lambda n is in the approximate point spectrum, we can get this. Now note that mod lambda n is less than or equal to norm Tn, and this is less than or equal to norm T for every n. That means lambda n is a bounded sequence. So it has a convergent subsequence. Let lambda n has a convergent subsequence. So let us denote this by the same sequence for notational convenience. So let us say lambda n converges to lambda as n tends to infinity. So it has a convergent subsequence. Let lambda be the limit of the convergent subsequence. Now what exactly we want to show is that we can consider t minus lambda I yn norm of this by a triangle inequality less than or equal to t minus lambda ni yn plus mod lambda n minus lambda norm yn, that is 1. So we know that t minus lambda n yn is less than or equal to 1 by n by the above construction of the sequence yn. This is plus mod lambda n minus. Okay. Now this converges to 0 as n tends to infinity. And we know that lambda is in the spectrum. So lambda is in the spectrum of T because spectrum is closed. So lambda n is converging to lambda, and each lambda n is in spectrum of T. So lambda is in the spectrum. So this implies this also. From this we can say that T star minus lambda bar I acting on yn, this also converges to 0 as n tends to infinity. Now from these two we can conclude that, let us look at this equation, this inequality norm of p t star minus p lambda bar identity on xn converges to 0. So let us call this equation 1. So by 1 we can say that, p of t star minus p of lambda bar acting on yn, this converges to 0 as n tends to infinity. Okay. Now what exactly you want to show is that p of lambda bar is exactly mu. So next consider p of lambda bar minus mu acting on yn. So this is less than or equal to p of lambda bar I minus p of t star everything acting on yn plus norm of p t star minus mu acting on yn. Okay. Now we know that p of lambda bar minus p of t star yn converges to 0 as n going to infinity. Now mu is coming from spectrum of t star, and mu is coming from spectrum of t star. So we can show that this mu of yn also p t star minus mu yn converges to 0, because the way we have chosen yns are coming from spectrum of yns are coming from the unit sphere of mn, and we know that norm of b restricted to mn is less than or equal to 1 by n. Now yn is coming from mn, so norm of b yn is less than or equal to 1 by n. Hence we can say that the second term also goes to 0 as n going to infinity. So from this we can say that mu is nothing but p of lambda bar. So we have taken mu from spectrum of p t star. So this implies spectrum of p P of T star is contained in P of lambda bar, where lambda is coming from spectrum, and we have shown the other way inequality earlier. So therefore we can conclude that spectrum of T star is set of all P lambda bar, where lambda is in the spectrum of the. So this is a polynomial version of spectrum mapping theorem for normal operators. Next we can ask, can we prove the continuous the spectral mapping theorem for continuous functions for the normal operators? So we can do that theorem in the next class. I'll stop here. Thank you very much.